the voltage and current drive capability. And there should not be a big miracle because we know exactly what we have defined. We have designed 0.9 volt negative excursion and 10 microamps positive excursion. So let's see if we make a plot what we get. So here you see the bias device again. And now I'm going to plot. I'm not going to plot all the characteristic. We are just going to do voltage to open circuit voltage and voltage to short circuit current. We could have done also the output characteristic. Well, maybe this is nice to do for yourself. You can build the circuit in the simulator, drive it with a current and measure the voltage across the current source. Then you have the output characteristic like IO, VO. The input characteristic is quite obvious for a MOSFET because there's no current flowing. So the input impedance is infinite. So there's no use of plotting that. But here you see what we have if we apply a voltage, and we change the voltage from minus 0.1 volt to plus 0.1 volt, and then measure the output voltage, the open circuit output voltage here. So you know this voltage change here would, let's say, cause, because of the biasing, a current flow in the FET, changing the output voltage. And if the output impedance was infinite, then it would be a straight line, like exactly vertical through the origin, but the output impedance of the MOS is not infinite. And here we see some interesting effects. Here we see the effect of drain-induced barrier lowering. Basically, when the voltage at the output becomes higher, then the output impedance becomes lower because the output current increases. This has been discussed in one of the previous lectures. And at the other side, we see that if we drive the transistor in saturation, so in the linear region basically, so we have a negative output voltage. You see almost 0.9 volt here. 0.9 is really the limit. So 0.9 volt, then this will be 0 voltage here, and the transistor will operate in its linear region, and the output impedance is much lower, and the transconductance is much lower, as I hope you know from device physics. So, and then you also have this flattening of this curve. So here we have a lot of voltage gain. Here it is less because of the left side. It is less because of drain-induced barrier lowering, and at the right side it is saturating to the output voltage because of the linear region. So notice that the voltage at the, is there someone who want to ask something? Because I hear, okay. Notice that the drain source voltage, of course, is the sum of the output voltage and VGS. So if we have here 1 volt, then we have already 1.9 volt at the FET, and this FET is designed for 1.8 volt. So at about 0.9 volt, which is here, about 0.9 volt, then which is at minus 50 millivolt input about, then this is the limitation of the device, basically. Now let's look at the next curve. The next curve is the short circuit current, so voltage to short circuit, and you see, oh, that's what I forgot to say, but here it's clear that it goes to the origin. 0, 0. And here also, this is what we expected because we designed the biasing as such, and this one is capable of sourcing 10 microamps and sinking much more. That depends, of course, on the device geometry of this transistor, because it's like 0.9 volt divided by RDS on of the device, and that depends on what your drive voltage will be. So here we already see the source capability, and that's what we also studied before, is limited by the bias source, and the sink capability is limited by the transistor. And of course by the load, but in this case we have a load of 0 ohm. And here you see that this curve is like a parabola. So this is like, it is working in the strong inversion region. We have a quadratic characteristic. We change the voltage, then the drop here, the current increases, but with a negative, with an offset and a negative and an inversion. So as a quadratic function. But here at the end, you don't see this quadratic function anymore. It appears to become linear. So we are having already short channel effects here. Velocity saturation and drain induced barrier lowering more or less set in at this voltage. I don't know which effect is more than the other. That depends on the model, and I didn't study that one for this particular device in detail. So then let's go to the dynamic, to the dynamic response, a large signal dynamic response. We now apply a pulse at the input, and the pulse is such, you see, minus 100 millivolt plus 100 millivolt, so we can have minus 100 millivolt. We are about here, let's say a little bit more than 7 microampere sources, and plus 100 millivolt would give us something like 12 microamp sink. So the source, of course, is delivered by the 10 microamp current source here, because if the transistor goes off, the bias source of 10 microamp delivers the current, and the sink is delivered by the voltage source, because if the transistor goes into a conduction, if the resistance drops, then this one can cause more current through the load, and that is the load is also its own internal capacitance, of course. So here we see a few nice things. This one, this peak, and the peak of the other one is crosstalk through the gate drain capacitance. You see, there's a gate between node 1 and node 2. There is the parasitic gate drain capacitance. And if you apply a positive step, then there would be a positive current at the output, so a positive voltage if you leave it open. And you see here a positive voltage, so a non-inverting response. The blue one is a step we apply at the input, and the red one starts with a non-inverting response. But after some time, the transistor takes over, and the transistor, the controlled current source, is inverting, and then you see it starts sinking current and it drops. And here it's the other way around. At the falling edge of the input signal, it's the other way around. Then first you also see the output falling because of the crosstalk. And the nice thing is you see here we have at the falling edge, we have a larger crosstalk than at the rising edge. And that has to do with the fact that we are here working in the linear region and the capacitance is much larger and the transconductance is smaller. So the zero is closer to the origin, as we will see later. This causes a right half plane zero. Inversion and differentiation together makes a right half plane zero. We will see it later in the small signal models that we are going to use. So at plus or minus 100 millivolt, I already told you, we have 7 microamp source and 12 microamp sink. And now we have a question for you. Which parasitic capacitances cause the slope limitation? Is it the gate source capacitance, the drain source, of the drain bulk, which is the drain source? Sorry, this should be the second one, should be drain gate. Oh, I hope you have a good one, because gate drain, yes, sorry, gate drain and drain. So the questions are good in the poll. And I have to correct my sheet again. You see, you can read it 1,000 times and still the errors stay. So that is a little bit surprising that 45% think that it is the gate source capacitance. And why is that surprising? Well, of course, we did not here draw the small signal model inside, so you need to do this yourself and understand. But the gate source capacitance is basically in parallel with two voltage sources. So A capacitor in parallel with two voltage sources is a pole at infinity we don't count. It's not a pole, it's not a free state of the capacitor voltage. So the gate source has no influence at all of the step response. Of course, we don't assume a gate resistance. We use a simple model here. Then we have the other two. Well, I don't know how this is in the poll, but the other two are right. So it's both CDS and CGD, because that is what the output has to charge and discharge. There's a capacitance between node 2 and 1, and between node 2 and 0. That is the capacitances that we are talking about. And this is the voltage on these two capacitors changes at node 2. So the voltage there is changing and it needs current. And that current is delivered either by the voltage source, the bias voltage source at the output, or by the current voltage source, but it takes time. And you see here we are discharging with the sink current of the device, and here we are charging at we will charge it with the 10 microamps. You could even measure the capacitance from it. Let's see, if you measure the rate of change and you are really sure that your input rate of change is short enough, is fast enough, then you can measure the falling and the rising edge and calculate the capacitors. If you know the currents, of course, but we know the current, we have 7 and 12 microamps. So you can calculate it from this. I did it, and it, of course, fits with model parameters.